In this video, we're going to work on adding interrupts into our operating system. And we're going to be doing this using a data structure that is known as an interrupt descriptor table, or IDT. And like our GDT, we have a nice page on the OS Dev wiki that can help us understand the structure of the actual interrupts and the interrupt table that we're working with. Now, inside of this interrupt table, we're basically going to have a bunch of different entries, just like we had with our GDT. And we're going to create structs for those, we're going to build up those entries, and we're going to implement them into our operating system. Now, the question is, what is really the purpose of an interrupt? And there's really two main reasons why we're working with interrupts. And the two main reasons are going to be for interrupt requests and interrupt service routines. So interrupt requests are going to be something that will typically come in through hardware. It's basically a request for the processor to interrupt its current operation or execution. Interrupt requests can come from a variety of different places. Some examples may be your keyboard, some different serial ports on your computer, and various different hardware components of your computer. So in order to be able to service these different hardware components, their communications with the CPU, we need to have some interrupt requests available in our operating system. Now, in addition to this, we also need to have interrupt service routines. And basically, these are the routines that are run when an interrupt is received by your operating system. So the operating system gets an interrupt. It needs to be able to do something with that interrupt in order to handle it. And the main ones that we're going to see in this video are going to be associated with errors in the operating system. So for example, if there was a divide by zero error in your operating system, right now, if that were to happen, the operating system would just crash. It wouldn't do anything, it would just go back to the grub screen like we saw with our GDT errors. Now, that's not really ideal. In most operating systems, it will crash and give us the error that occurred. We could see this in Windows with the blue screen of death, and we could see this in other operating systems with things like kernel panics. Generally, what we'd like to do is display an error to the user to say, this issue happened, and here's the information about like the stack and the registers, that sort of idea. For this video, we're really just going to demonstrate the message to say, hey, this exception has happened, and here's what we want to do about it. So with that being said, let's get into the actual implementation. Now, a few things have changed a little bit from this code. I just put everything inside of this source file, that's source code, just to help to organize it. And for this video, I'm going to put all my interrupts code inside of its own folder. This is going to help me organize things a little bit more. You don't need to do this. It's just for me to keep track of everything. But we're going to create three files associated with interrupts. There's the idt.c, h, and s. S is our assembly code, which we need. This is our C code, and this is our header. So we'll start inside of the header. And like I said, like the GDT, we're going to have a struct for each entry inside of the interrupt table. And these entries are going to have a very specific structure associated with them, which you can see here inside of the OS Dev wiki. You'll see here that, like the GDTs, we have an offset, which is divided up into two pieces. This offset is the entry point of the interrupt service routine. So it is the function that we want to call when the interrupt occurs. So interrupt occurs, we go to that offset and start executing. We have this P, which is the present bit, like we had in our GDT. It's set to 1 to say that the descriptor is valid. We have a DPL, which was also present in our GDT. This is the 2-bit value that represents the CPU privilege level. We'll typically set this to 00 to have these at kernel level. We have this bit that's always going to be 0. We have a gate type, and a gate type is going to be something that describes the interrupt that we've added in. We're always going to see this as a 32-bit interrupt gate, so 0xe is the one that we're going to be using for these entries. We have a bunch of reserved space that we don't need to worry about, and then we have a segment selector. The segment selector allows us to specify a code segment in the GDT that we are going to use for this particular entry. So this is something that we're going to set towards a valid code segment in our GDT. So understanding that idea, we'll just put in our struct, and as with our GDT, we need to make sure that the ordering and the formatting is the exact same as the one that was specified in that wiki. That'll just make sure that we don't have any sorts of errors or problems with the formatting here. So I'm going to implement each of the different properties that I have. And this sort of thing is very similar to our GDT entries, so it's not really anything too exciting. It's pretty standard and straightforward. And we're going to, like before, set the attribute as packed for these. Okay? So that's the setup of the entries. Now, like our GDT, we are also going to have this pointer struct, which is going to, of course, point to our IDT entries. So this is the same sort of idea as what we had with the GDT. So we have a limit and we have a base. And this is, of course, going to have an attribute as path. Now, for now, there are two functions that we're going to work with, one to initialize the IDT and one to set each of the IDT gates. This one is going to have a very similar structure to the GDT. It's going to have the index in the array where we're placing the actual gate. It's going to have the base value. It's going to have the selector values, the select values, and we're going to have the flags as well. So those are the three things we need to provide to it. And what we're going to do is we're going to do some bitwise operations to parse things out and get it into this format here, which we'll see as we're going through. So I'm going to go ahead and copy these over to idt.c, just that way I have both of these function descriptions in and available. And then we'll get to work with our implementation. Okay, great. So in order to set this up, we're going to need a few different things included. We're going to include our standard int. That way we get over like uint formats, these types of things. We're going to include the util.h. So we need some utility functions as we're working through this. We're going to need some VGA functions, so we'll include our VGA header. And of course, we'll include our IDT. There's two structs that I'm going to initialize here. We have the IDT entry struct, which I'm going to call IDT entries. It will have 256 in size as the array. So there's going to be 256 entries in the IDT. Not every single one of them is going to have a value, but some of them will. So we'll see how that is structured out. And I'm going to define the struct for my pointer, which is just going to be called IDT pointer. Okay. And then I'm going to create an external reference to a function called IDT flush. This is similar to the GDT flush. It's going to be some assembly code that's going to essentially set up all of these different records that we're creating inside of the IDT table. Now, there's a few interesting things that happen with our IDT. The very first thing that we're going to do is set up the limit of the pointer and the base of the pointer. This piece is quite similar to our GDT table. So we're just going to get the size of each of the structs and multiply it by the size of the array. So these two numbers here are going to match with each other. And then we subtract 1, just like with the GDT. Similarly, when we set up the base, we're just taking the address of IDT entries. So the address of this array right here. And then what we're going to do is we're going to initialize everything to 0 using memset. And that's because we're not going to set a value for every single entry here, but we do need the total number of entries initialized. So we're just going to initialize everything to 0 and then set the ones that we actually need. So this is going to be the size of the IDT entry struct times 256, just like that. Okay. So all of this is very standard, straightforward so far. This is where we get into the interesting part, and it's the fact that we need to actually do some programming for what we call programmable interrupt computer, or PIC. So in your computer, there are two PIC chips, and generally they'll have different namings for them. I think like the standard naming is that one of them is called the master chip, one of them is called the slave chip. You could also refer to them as the main chip and the secondary chip, whatever you want to refer to it as, but you'll see those terminologies generally used for these chips. Generally, one of the chips is going to sit at memory addresses 0x20 for commands and 0x21 for data. The second chip is going to set at 0xa0 for commands, and it's going to sit at 0xa1 for data. Now, these will need to be initialized in order for us to be able to use our interrupts. So we need to actually send some data to these chips. Now, how do we send that data? Well, we have to use a special command, which I'm going to set up in this util.c. That special command is going to be called outport_b, that's what I'll call it. It's going to take in a value for a port, and it's going to take in a value. And what it's going to do is it's going to run the following assembly code. It's going to run the command outb, %1, %0. And then for the syntax, we put this. And then we put the formatting of our value for the port and our formatting for the value. So you may not have ever seen this operation before. I never really talked about it in the x86 video so far. What it does is it outputs a byte of data to a specified IO port. So what happens is all of these different ports on your CPU could be hooked up to different chips. So one of them is hooked up to those PICs. And what we're going to do is we're going to write data to the port that's hooked up to those PICs. So we could send data directly to those chips. That's the idea of what we're doing with this port value setup. So we're writing to the port associated with those chips a specific value. And that value is going to be for the initialization of those chips so we could set them up for our actual interrupt creation, okay? So that's what we're looking to do here. So that's what this function's purpose is generally going to be right now. The reason why I put it in util is because we will use it in a variety of different places, not just in the IDT. So we are going to set it up here and then just import it wherever we need it. So as I mentioned, these different ports are going to be associated with each of the different areas on the chip. So to get this to work, what we're going to do is we're going to run out port B. And the very first thing that we do is we send 11 to the command ports of each of our chips, the primary and secondary ones. So we send 11 to each of those chips. This is going to start those chips up into their initialization mode. So now they're waiting for, I believe, 3 more commands they'll accept. And each of those commands represents something specific. It's going to give it an offset, and then it's going to give it the location of each of the different chips and initialize those. And that is going to get us all set and ready to go. So that's the first set of commands that we need to do. Second set of commands that we're going to do is the following. We're going to send to the data section of the first chip the value 20. And then we're going to send to the data section of the second chip the value 28. So these are what are referred to as the, I believe, vector offsets. So it's setting up those offsets for our chip. And then we're going to send a few more requests out to these data sections. Okay. So again, we send off to each of the data sections. In this case, the values 4 and 2. And then we're going to do a few more data section sends. So we have another set of those here. So we send to 21 0x01, and then we do the same with 0xa1. We send it 0x01. And then finally, as the last sort of thing, we just send zeros to each of these different chips. Okay. So this is the conventional way that we are going to initialize these PICs so that they are available for our interrupts. So this is how we initialize those values. Okay. From here, everything is going to be pretty straightforward. We're just going to be setting up the gates for all of our different interrupts. Now, this process is a little bit tedious, I'll admit, to set up these different values, but we'll try to get through it as quickly as possible. So what we're going to do is we're going to set the IDT gate. Again, we provide a number, and then we provide an actual function for it to use. Now, we haven't implemented any of these functions yet, and we'll do that. We're actually going to implement them in assembly. We'll number each of them based on their actual service routine number. So they'll be 0 through to 31. There's 32 total functions that we're going to implement here. Now, before I get into that, I just want to explain to you how we set up these two flags, the SCL and the flags here. First one is 0x08. The second one is 0x8e. Let's talk about what each of these are representing. So for 0x8e, what this is representing is we would have the following. We'd have 1 0 0 0, 1 1 1 0. This top half here is going to be the present bit, which is set to 1, and then the DPL, which is set to 2 zeros. And then this bit here, which is always 0. So that's what that first 4 bits is representing. The last 4 bits is the gate type, which, as I mentioned, is always equal to E, right? Because it's a 32-bit interrupt gate. So that's how we got this piece here. That's the E, and then this is the other bits. For the present bit, the DPL here, and then this bit is just always 0. So that's where this 0x8e is coming from. The other one, 0x08, what that is it's really just like a simple one here. It's just set to 0 0 0 0 and then 1 0 0 0. What this is representing here is the code segment associated with this. So this is really looking at the selector here. So the selector has to point to a valid code segment in my GDT. That valid code segment is 0x08, which is the code segment that we've initialized in our GDT. So that's why this is equal to 0x08. Now at this point, what we're going to do is we're going to copy this, and we're going to do this a whole bunch of times. All that's really going to change is that these zeros will change to 1, 2, 3, and then this will change to 1, 2, 3, and you're going to do this a whole bunch of times. You're going to do this about 32 times. So in the sake of time, I'm just going to go ahead and copy these, and I'm going to paste them in. You'll see that they're all the same in terms of entry. The only things that change is this number here and this number here. And I'll make this code available so that you don't have to go through the process of typing this out yourself, because it's extremely tedious and you're not going to learn anything from typing this out. So you can just copy and paste it, no big deal. Now, similarly, we need to make reference to all these different functions. So inside of idt.h, what I'm going to do is I'm going to set up an extern void to each of these different functions. So we'll do ISR 0, and then, of course, we'll do ISR 1, and this is going to repeat over and over. And like I said, I'll give you the code so that you don't have to type this out one by one. Just copy and paste it. It's not really worth typing out. There's just the same function, just with these numbers here. Okay, so that's nice and easy. Now, there are two other interrupts that we would typically implement here, and they're for system calls at 128 and 177. So there is a fairly big jump here, but these are the ones that we would use for system calls. Typically is the ones all the way out at 128, 177. And I'll just go ahead and place those in here as well. They look the exact same. They're just used for system calls, which is why their numbers are higher. Okay, so far so good. We could set our IDT gate here, make this all set and ready to go. The actual way that we set each of these gates is pretty straightforward. We just do some manipulation for the base low, which we do using, of course, our typical bitwise operations. And we'll do the same for base high right here. We'll shift it by 16 and then AND it with 0xFFFF in order to get us to the high bits. Now to get the values for, the SCL value here, we simply just set it. In order to get the value for always 0, we really just set it because it's, of course, always 0. So that's nice and easy. And then in order to get the flags, we're just going to take that flags value and OR it with 0x60. All that's going to do is it's just going to remove the other bits that are inside of that variable there. So you see that flags we have right here. When we're defining that here, we have a few different pieces that are associated with it. So we just OR it in order to eliminate any unnecessary flags. And that gives us our IDT flags. So that's all good. Now, last thing that we need to do here is an IDT flush, which you have defined as an extern function, and we'll have to implement that inside of our assembly code. We're simply just going to give that a pointer to the IDT pointer, and we'll be good to go there. So that's our setup so far. Let's go over to our assembly code and set up some of the other pieces that we need. Now, we have to be a little bit smart here with the way that we set things up. First off, easiest one is IDT flush. Okay, this function is not really too complicated. Same sort of process as what we saw inside of our GDT. All we do is we just extract off the argument from our stack, and then we run this command here, lidt, using EAX. That's going to load the interrupt descriptor table using that pointer that we've provided. And then we can do STI. What this does is it sets the interrupts. Right now that we have interrupts available, we can turn them on and we can use them. And then we just return. So that's all we need to do for the IDT flush. Now, as you see in our header, we've defined all of these different ISRs, and they're all external, which means that they're all at an assembly level. We need to implement all of these. So one way that you can implement them is you could, write out the definitions for each of them and copy and paste and write out 32 functions, and, eventually you'll be done. But there is an easier way to do it. It turns out that there's really two different kinds of interrupt service routines that we would typically have. The first one is one that has an error code associated with it. So basically an error code is associated with that interrupt. So we are able to use that error code. And then the other one has no error code. So we actually have to just generate like a dummy error code so that the argument is available for us to be able to work with our service routine. So the way that we can define these is actually using macros in assembly. So a macro is defined just by putting %macro, and then we give basically the name of the macro. So I'll call this one the no error code, and I'll put a 1 here. The way that this works is basically we'll create a global definition and we'll name this ISR %1. Whoops. So basically whatever value is provided as an argument will be placed inside of here. So if I give this ISR no error code 0, this will become ISR 0. So do you see how that would result in us getting every single function defined, right? And then we can implement it right here. I can do ISR %1. And all this is going to do is it's going to, first off, do CLI to turn off our interrupts or clear our interrupts. We're going to push on a basically fake error status or error code associated with this. So we push on that 0. And then what I'm going to do is I'm going to push on the value of %1. So those are the two arguments that are required here. And then what I'm going to do is I'm going to jump to what I'm going to call the ISR common stub. We'll have a common set of code that's going to handle all of our interrupts. So we'll define that in here a bit later on. So that's the end of this macro. Now we're also going to have a macro that's going to be associated with our error codes. So ISR error code, we give it a 1. We're going to do a global ISR %1 like we did before. Again, ISR %1. We're going to do a CLI to set up the interrupts. We're going to push long %1. And then we're going to jump to the ISR common stub. So do you see that the only thing that changed between these is that we just don't have to push this onto the stack, right? That's because the error code is already there. So we only have to push this one value on before we jump here. That's the only difference between these two macros here. Now there will be another macro that we'll define here, but we'll get to that when we talk about interrupt requests. So we'll just leave it like this for now. And then to define each of our different ISRs, we simply just say ISR and then whichever macro we want to use. So for instance, the first interrupt service is 0, and it's a no error code one. So I do ISO no error code 0, and it will generate the ISR 0 for me and give it this code. Okay. We're going to have an ISR no error code for 1. Or sorry, this should be no error code for 1. And we're going to continue to repeat this over and over. Now I can't necessarily just copy and paste this and say that there's not really too much work to do, because there are a few different ones that we have to sort of set up in specific ways. So up to 7, we have no error codes. Then when we get to 8, we do have an error code. So 8 is going to have an error code. 9 is going to have no error code. But then 10, 11, 12, and all the way up to 14 are going to have an error code. So 10, 11, 12, 13, 14. These will all have an error code on them. So this will be 11, 12, 13, and 14. So those are all error code ones. And then we have a whole bunch more that have no error code. So all over the rest, from 15 all the way down to 177, are going to have no error code associated with them. And this is the way that we set up our interrupt service routines with error codes. Now, next after this, what I could do is I can set up my common stub. So I'm going to create an external reference to a function called ISR handler. This will implement in C, but the ISR common stub will implement in assembly. What we're going to do is we're going to push all of our registers onto the stack. We're then going to move into EAX the register DS. We're then going to push that onto the stack to preserve it. We are also going to move CR2 onto the stack through the same sort of method. And then what we're going to do is we're essentially just going to move our AX into, or we're going to move 10 into AX. And then like we often do, we're going to initialize our segments. So we're going to initialize our data segment to that. We're going to initialize ES to it. We're going to initialize FS to it, and we are going to initialize GS to it, okay? Then we are going to push onto the stack the ESP register, right? That's our stack pointer in this case. So what we've really done is we've placed all of the relevant registers associated with this interrupt onto the stack. And what's going to happen is we're going to call a function called ISR handler, which we're going to implement in C. And that's going to get all of that information. And it's going to be able to use that information to tell the user, what the values were of these registers in stack before this actually happened. That's mainly what we're doing here, okay? So next I'm going to return back from this function. So I'm going to add 8 onto the ESP. I'm going to pop EBX And I'm going to go ahead and move that back into each of my different registers here. So we're going to move these into each of these here, ES, FS, and GS. So that's the way that we're generally going to set things up here. Now, as I'm looking at this, it looks like maybe this shouldn't be DX, but rather should be DS. And I'm just going to confirm that here quickly, just to make sure that I've got that correct, because it looks like that might be, yeah, that was just, I think, a little bit of a typo there, right? So yeah, it should be DS. So DS, ES, FS, and GS. So those should be the values there, okay? From here, what we're going to do is we're going to then pop all of the registers off using pop A. We're going to add to the ESP value 8. We're going to do an STI, and then we're going to do an I return from this. And that's going to be what we need for this common step. Now we're getting very, very close to having our interrupts wired in here. A few final steps that we're going to need to do is to deal with this ISR handler. So this ISR handler is going to be set up inside of our header file here first. So ISR handler, which is going to take in a struct called interrupt registers. And we're going to implement this inside of our idt.c file, okay? So let me copy this over and I'll just paste it here for me to use. Now we need to, of course, implement this struct called interrupt registers. I'm going to implement that inside of my util since I will use it in a number of different places. And the struct will be called interrupt registers. And like I said, it's really just going to store all of the different registers that are associated with an interrupt. So you see that we're going to have the data segment, the CR2 register. We're going to track the values of the EDI, the ESI, the EBP, the ESP, the EBX, the EDX, ECX, EAX. These were all pushed on by that push A command, right? We're also going to have an interrupt number. Remember that we are providing this from the ISR numbered functions, right? ISR 0, ISR 1. They're each going to have an interrupt number and an error code associated with them. And then, you know, aside from these registers here, we also have a few related to EIP, the CS register. We need the eFlags register. We need the use resp register and the SS register. These will be pushed by the processor automatically for us. So we'll have all this information available, okay? So we come back over to our ISR handler. What we're going to do is we're going to print out a message based on the interrupt. And generally what this involves is I'm going to create this list of different messages based on each different interrupt. So we can discuss all the different interrupts that we have available and what we're going to do about them. So we'll have this exception messages. We'll have a few different types. So a 0 would mean division by 0 occurred. A 1 is what we call a debug interrupt. Next would be a non-maskable interrupt. Then we have a breakpoint. We would have an into detected overflow. And all these are really just standard kinds of interrupts. So if you were to look up an interrupt table, you would see these kind of interrupts specified in this exact order, right? Each one has a specified number associated with it. So we can use each of these. And some of these are probably, familiar types of terminology, right? Like invalid opcode would be, of course, we have an invalid operation in our code, right? Things like a double fault and triple fault were things that we had discussed as we were sort of going through our actual process here. So we would have our double fault here. We could have a coprocessor segment overrun. We could have a bad TSS segment. We could have a segment not present. We could have a stack fault. We could have a general protection fault. There could be a page fault. There could be an unknown interrupt. There could be a coprocessor fault, an alignment fault. And then the last one here is just called a machine check. And then the remaining ones that we have available are all just reserved. And I'm just going to copy these in. There's a bunch of different ones that are available. So from lines here 104 to 116, we see that the remainder of these are just reserved. And all our ISR handler is going to do is it's going to take a look and it's going to say if the register's interrupt number, so it's going to pull the interrupt number. If it's less than 32, then what I'm going to do is I'm going to print using my VGA the exception messages associated with that interrupt number. So it's going to grab that interrupt number, it's going to print its exception message. And then what I like to do is just sort of print out like a new line and then print out a message that just says exception system halted. And generally we'll halt the system here. So to do that, we could just put in like an infinite loop like this, and we are good to go. So this is going to take, if we have an interrupt that we recognize out of any of these, it's going to give us that exception, and it's going to say, oh, we've encountered an exception, and the system has halted. And with that, we now have all of our interrupts actually set up. So the last thing that we'll need to do for this process is to implement our IRQs, or our interrupt requests. So the interrupt requests will be the next thing that we'll take a look at handling here. To implement the interrupt requests is going to be fairly straightforward. Basically, it's going to take up some of the remaining slots that we have here from the 32 gates that we've added so far. So basically, when we're taking a look at this ISR handler, the reason why it stopped at 32 is because everything past there is going to be an interrupt request instead of an interrupt service routine. So an interrupt request, as I mentioned, is going to be related to hardware. So things like keyboards and other devices may send interrupt requests to the CPU to ask it to interrupt its execution. We'll see that process in more detail as we continue to implement different hardware components like keyboards and drivers related to those. So to start off, let's take a look at how we can get these interrupt requests set up. So generally the way that this is going to work is going to be very similar to our interrupts that we already have. So we're going to add in some new interrupt gates, the exact same gate style, and frankly, the exact same syntax, right? So rather than using ISR as our syntax, though, we're going to change this to IRQ. So rather than saying ISR 0, we're going to say IRQ of 0. These are going to go the same way, 0x08 and 0x8e, right? The exact same values, just this changed to IRQ 0 rather than ISR, since these are now interrupt requests. And as I mentioned with these, really it's just a process of copying and pasting. You're going to do this 16 times to get 0 through to 15. That gives us our 16 interrupt requests that are going to be standard for our system. Now, in addition to this, inside of our header, of course, we need to create external references to these functions. Same sort of process as the ISRs, it's just an external void, and then IRQ 0 through 15 to match the functions that we require. Now, we're going to implement these inside of assembly, and we're going to implement them using these macros like we did before. So generally what we're going to do is we're going to set up a new macro for our IRQ. It's only one kind of IRQ. We don't need to create like an error code, non-error code one. We just have a single one. Now, I think I forgot to mention previously that this one indicates that there's one argument provided. So this one argument here, and it gets plugged in at this %1 sign. With the IRQ, there's two, so we use 2 here. And basically, one of them is going to give us the IRQ number, so we can create all these different function names like this. And then the other one is just going to be used as our value that we push on as an argument. So that being %2 right here. And you can see everything else works pretty well the same way. We create the interrupt, we push a 0 on. This is similar to this non-error code version here. We then push on the IRQ that we are given, and then we're going to jump off to where we're going to call the IRQ common stub. Just like this. And then with these different error codes right here, we're simply just going to define our IRQs. The IRQ has 2 arguments, so 0, 32, for instance, is going to be our first IRQ, and it's going to have a value of 32. Remember, these start just past the ISR, so the ISR ended at 31, so these begin at 32. And you're going to repeat this process 15 times. I'm just going to copy it in because it's, again, a lot to do and not really much benefit to see me type it out, right? So you see here we just have 32, 33, 34, all the way up to 47. There's 16 total here. Now the IRQ handler actually looks very similar to the ISR handler. For that matter, it's pretty well fine for me to just copy this here, and we just need to change up a few small things inside of it to get it to work. So this is going to be referencing a different function called the IRQ handler. We're going to call this the IRQ comment stub. It's still going to do a push A. We're going to move these different registers onto the stack. We're going to take 10 here all the way into all of these. We are going to push the ISP. We are going to make a call to IRQ handler instead of ISR handler. And all of this looks good to stay the same. So that's all we really need to do there. Now coming back to the IDT is where we're going to actually implement that function, as well as a few others that are going to be helpful. So the IRQ handler is going to work like this. We're going to create, first off, an array of what we're going to call IRQ routines. This is going to keep track of all of the IRQ-based functions that are going to be associated with these interrupt requests. And we're going to start off by zeroing them all out. And I like to divide this up basically so that there's 8 on each row. So 4, 8, and then down here, 1, 2, 3, 4, 1, 2, 3, 4, just like that. So this gives us the 16 routines that are associated with our interrupt requests. And basically the way that this is going to work is we're going to have two functions here. One is going to be called install handler. And what this is going to do is it's going to take in an IRQ, and it's going to take in a handler function that uses the interrupt registers as an argument. And all it's going to do is it's going to associate the routine that was provided with the handler function that was provided. And for people who have some high-level programming experience, this is kind of like an event handler, right? We are basically associating an event with a function that's going to handle it, kind of like a callback, right? Same sort of idea here. We're saying if this interrupt request comes in, this is the function that handles it. So the idea is that when we create a device, say like a keyboard, we can register it with an interrupt. And what's going to happen is when that interrupt happens, we have the function to handle it, and we're going to be able to handle it through this install handler. So you'll see this process being used fairly often. And in some cases, we may need to deregister or unregister, or in this case, I think we call it uninstall usually. And to uninstall, we simply just make a call to this function here. It's going to take in an IRQ, and it's simply just going to set that IRQ back to 0. So that's the way that we uninstall these handlers. And then the final piece here is if we hit that IRQ handler from the routine that we defined, again, like previous, it takes in this interrupt register structure. And what it's going to do is it's going to get that handler that's associated. So that interrupt set here that we have. And it's going to say the handler is equal to the IRQ routines at the registers int number -32. Okay? So we're going to take that, we're going to minus 32 in order to get one of the indexes inside of this list here, right? Because remember, the interrupt number is going to be starting at 32. So we take 32 and subtract it from that value in order to get into this array here, okay? So that's how we get into the array. If that has a handler associated with it, so if there's a handler function, we are simply just going to call that handler function with the registers that we have. And then in general, there's a few special sort of cases. If the interrupt number is greater than or equal to 40, we actually have to send out a signal to 0xA0 with a value of 20. And then in all cases, we have to also send out a signal to 20 with the same value, like this. So this is always required for our interrupt handlers, just to send those signals out to, again, our PIC. So this would be the general setup of our interrupt requests. And at this point, we should have everything up and running. It looks like I've got everything wired in. So let's go over to our command line. Let's try to make and just fix any errors that have inevitably creeped up here. So it looks like I've missed a comma in my register declaration. That would be just over here at my util.h. Yeah, just missed this comma here. So that's not so bad. And then what we're going to do is just keep looking at some of these different ones. It looks like there is a semicolon error in my GDT. And let me just take a look at this here. This is just before, looks like just before GDT flush for the X turn, reference to it. Yeah, so we see here, X turn void GDT flush. It's likely something that has happened just outside here. So it looks like that's fine. It might be inside of the GDT struct that we have the problem. Looks like all of that is generally fine. Let's just take a look here. Actually, the error would be just in util.h. Yeah, I just forgot a semicolon here. So that looks to be the problem. So let's just do another make here. And I get this other error, junk dx after register, and likely all this is in util.c. I've just forgotten a comma here. So that should fix that problem. Make one more time. There we go. Looks like everything is making successfully. Now we can add in our interrupts into our make file to get those to make as well. So we'll gcc, we'll do c flags -c. So the value is in source / interrupts / idt.c. I'll call this idt.o. And then we also have an assembly file associated with that. So elf32 source / interrupts / idt.s. And I'll call that idts.o. And actually, oh yeah, I put a lowercase I here, so we'll just keep that nice and consistent. And then right over here inside of our object files, we can of course get these looped in, so idt.o and idts.o. And let's go ahead and try to make this and see what happens. So when I do a make here, we're going to see a few different errors. So one of the errors actually comes out of the fact that inside of our util.file.c, we are having this standard int.h imported in the header file instead of the C file. So if I move this over to the C file, it will reduce the redundant imports, because you'll see here that you get some conflicting types because both IDT and util are importing the standard int header. So when we fix that, it will fix up a lot of these errors for us. We'll be left with a few smaller ones that are more manageable. So first off, this one here in memset, I just forgot the struct keyword. So we'll just go ahead and fix this one up here. So if I come over here, you'll see right inside of here, size of, this should be struct. I often forget that keyword, so fix that up. A few other things that I noticed here is this star is in the wrong place. It should be char star. And there should be a semicolon after this here. That'll fix up a few other errors. So let's go ahead and make. And we'll see we have one more. Reg is not defined. It should be regs, registers like this. And that should fix that up for us. Okay. And we can see here that we have one other error related to our macros here. The expected an end of file at line 144 in the macros. Let's go over to gdt.s, or sorry, idt.s rather. At 144, it looks like we were having some troubles with this compiling here. So when I'm taking a look at my macros, I just want to make sure that they're all defined in a consistent way. It looks like they are. Now when I'm taking a look at this, I just want to see, are there any sort of things inside of this file that look a little odd? End of file while still defining macro. Oh, I probably forgot the end macro. That's probably it. Yep, that is it. There we go. So I need the end macro here. And that'll fix that up for us. And now it looks like everything builds fine. So to test this out, what we're going to do is we're going to go into kernel.c. I'm going to include my interrupts, idt.h, like this. And what we're going to do is we'll do an init idt to initialize our idt. And basically, we should just see nothing crashing would be ideal. So let's go ahead and launch this and see what happens. Might take a few to get to it. There we go. And as you can see, it doesn't crash, so that's a really good sign. Now, one thing that we could do to test this is get an exception to throw. One exception that we have is 1 divided by 0. If I try to print that onto the screen, I should see an exception occur. Let's give that a try and see what happens. Do you see that we get division by 0, exception, system halted? That's great. That means that that exception was caught, it was handled, and we printed this out onto the screen, and we halted the operating system. So with this, all of our interrupts are now set up and ready to go. So we're able to use these interrupts now, and we're going to use these in the next few videos to start to wire in some of our hardware into the operating system. So thanks so much for watching, and I'll see you in the next video.